Welcome. In this lecture I want to look at von Neumann's method for analysing finite difference schemes. So in a previous talk I showed that there are simple numerical schemes for calculating, say, advection of density by a constant velocity, and that these are sometimes stable, so they produce solutions which are smooth, which vary in a physically reasonable manner. And then there are other cases where, with a small change of input parameters, say from a positive velocity to a negative velocity, these same schemes can produce completely unrealistic values, so big oscillations and rapidly growing modes. And here I want to introduce this idea of stable and unstable numerical schemes, and a relatively simple but quite powerful method from von Neumann, which can be used to understand when these schemes are stable and when they're not. So the basic idea is that you have a numerical scheme which approximates a finite difference set of equations, and that this method is stable if the waves you're interested in studying, or the phenomena you're interested in studying, are not completely dominated by growing modes which are purely numerical. So in your system you'll have waves which are physical, which correspond to physical reality, and then there are waves, or there are types of oscillations which are not physical, which are just because you have a particular numerical method. And some of these waves can grow, and in some cases this can then dominate your simulation and end up producing an unstable method. And so in general you have methods which are either unconditionally unstable, and there are quite a few of these. These just mean that no matter what you do, any input parameters will be numerically unstable and produce essentially gibberish. So these should not be used. In very rare cases you find unconditionally stable methods. These are extremely rare. Usually only in particular limited cases methods will be unconditionally stable, so it's not unconditionally. Or you have to make some assumptions or simplifications so that the equations you're solving are stable but not necessarily the same as reality. And finally, the most common case is that methods are conditionally stable. So there'll be some conditions you have to satisfy, some limits on the parameters you can use, but if you stay within those limits, then the method should be stable and should produce a sensible answer. So the various what we want to do is find out what those limits are. When can we apply our methods? When will they produce good results, and when will they not? And so this is the idea behind von Neumann's scheme. So von Neumann's scheme is a way of analysing numerical methods. So von Neumann's method. And what we want to do is take our numerical scheme. So what we had before was, we had, say, the density equation, and it's evolving in one dimension in, say, x. So we have ux is the speed in the x direction, and then we have a d rho by dx. So if you approximate this with a simple forwards finite difference, so d rho by dx evaluated at a point xn, we said that's approximately rho at xn plus 1, so it's the next grid point minus rho at xn divided by the distance between the grid points, or the mesh points. So we have a one-dimensional system with x. We divide it up into space. Here we have xn plus 1, and we have density is evaluated on these points here, and then the spacing here is delta x. Okay, so this is the simple approximation we used. And we found that in this case this was stable and produced sensible results if ux was negative, but if ux was positive, it very quickly blew up and produced unstable results. And so here we can use this method to understand why. So the basic idea is that we take this finite difference approximation and we make an ansatz. We say that the solution rho, which is a function of time and space, is some kind of amplitude which depends on time, and then a wave has some kind of wave character, so e to the I kx. So it depends on space through this kind of wave, and then it depends on time through this amplitude. And then this will allow us to look at what happens for different k. So this is the wave number k. And so we can put this into the equations. In particular, a useful fact of this then provides a way of transforming these finite difference formulae into continuous functions that we can look at. So, for example, rho at x n plus 1 we can write is just a of t, so I haven't changed the time, so e to the I k x n plus 1, and now this x n plus 1 is just the next mesh point to xn, so the distance is delta x, so this is just we can just write this as xn plus delta x, and so we can substitute this into this formula here, so let's put that into here, and we just write this as a of t e to the I k x n, and then we have the plus delta x term, which just becomes an e to the I k delta x. And so we can take this formula and we can substitute it into our finite difference approximation here. And so we have d rho by dt, which is just, so d rho by dt is a dA by dt, because that's the only part of rho that depends on time, times the e to the I kx. And then here we have a minus ux, and then multiplied by the finite difference formula. So here we have a rho xn plus 1, which gives us this a of t e to the I kx xn, so this is a xn e to the I k delta x. So minus rho at xn, which is just a e to the I k xn, all divided by delta x. So this we can then simplify quite a lot, because this e to the I k xn appears everywhere, as that all cancels out. We can then simplify this a bit, because a can come outside here, and so we just end up with dA by dt is minus ux over delta x, multiplied by, here we have an e to the I k delta x plus 1 times a. That's actually this, so a depends on time, but this part here, this does not depend on time, so I'm just going to call this, let's say alpha. This is just not even a function of space, this is just a value which depends on k. So if you have a given mesh spacing, a given velocity, each different wave that we're putting in will have a different k, and so this alpha will in general depend on k. And so now we can just write down that we have a dA by dt is minus alpha a. And so the solution a of t is just a naught, some constant, times e to the minus alpha t. And so if alpha is positive, so if alpha is bigger than 0, then this will decay. So a of t shrinks or gets smaller in time. So it basically goes to 0 as t goes to infinity. As t goes to infinity. But if alpha is larger than 0, then if alpha is less than 0, then this is positive, and then this will exponentially grow. So therefore a of t grows. And this is an unstable case. So what we have to show is that for every k in the system, that this is true, that alpha is bigger than 0 for every k. And in particular, in this case, what we care about is the real part of alpha, because here this can be imaginary, we have imaginary components, But if we have an imaginary component here, it just means you have an oscillating amplitude. And what we're looking for here is growing or shrinking amplitude. So we'll just take the real part of alpha. So the real part of alpha is the real part of this expression. So we have a ux over delta x over, and then we have an e to the ik delta x minus 1. So this is a cos k delta x minus 1. Okay, so in this equation, this cos k delta x is between 1 and minus 1. So it's basically between 1 or minus 1. And in any case, this cos minus 1 must be between 0 and minus 2. Cos k delta x minus 1 is basically less than 0 and greater than minus 2. So it's somewhere in that range. The important point though is that it's less than 0. So if this is less than 0, and we need alpha to be positive, or the real part to be positive, then ux must be, so therefore ux must be less than 0 for stability. So this has shown mathematically the result that we found numerically is that if you have the wrong sign, so if ux is going the wrong direction, then we have an unstable system. And we can understand a little bit physically why this is happening. And this is the consequence of sort of upwinding. So what we have is, if you think about what the system is doing, you have a set of grid points here. So this is xn again, xn plus 1. So if we have a system where the flow is negative, so ux here is less than 0, which is the stable case, this is stable, the rate of change of this quantity with time depends on this quantity here. So we're using values here to calculate what happens here. And physically this makes sense, that we're taking information from this grid point and we're using it to calculate and update this value here. And this is physically what's happening in the real system as well, that fluctuations or matter is flowing from here to here. And so information is flowing in the same direction in the simulation as it is in the model, as in the real life. So the opposite is if we have downwinding, and this is the case where we have the flow is reversed. So if ux is bigger than 0, then we have a case where we're using, this is again xn, we're still using this point, xn plus 1, to calculate and update the values here. And so in this case, the flow coming up from upstream, the information about what is coming from this flow is not used to calculate the value on this grid point. And so the information flow required to understand what's happening to this wave is not being used in the same way. So we have information flowing this way but not flowing that way. And this ends up being unstable. Okay, so there are various ways around it. Some schemes use both directions, so you can use both upstream and downstream simultaneously. As long as you have some points upstream, then you remain stable. It's only when you go to a case which is completely downstream, downwinding, then you end up very unstable. Okay, so one limitation is that in this work we essentially assumed that the finite difference scheme in time was perfect. So we didn't make any approximation to this time derivative here, only to the spatial derivative. In a real system, there is a numerical method being used for time integration as well, and so that also introduces its own limitations. And so that I'll look at in another video on the CFL condition. Thank you.